Hello, I am recording this video on multiplexer and demultiplexer circuits. It is a part of our experiment 9 in analog and digital electronics. This is probably my final year, so I am recording this. As you can see, the multiplexer and demultiplexer circuit arise from the need of electrical communication. In electrical communication, you can send only two things. One is for 0 and another is 1. 0 means there is no current in the circuit and 1 means there is some current in the circuit. That is the idea of this electrical communication. The first known example was telegraph. In telegraph system, as you can see in the picture, it is like a piano. And there are 26 different keys because of in English there are 26 alphabets from A to Z. So they used to press one key. It means that suppose for first key that they will send A, and for the last key they will send Z. Now, in order to do such kind of communication through electrical contact switches on and off, the problem was you have to connect 26 lines between the sender and receiver, which is not a practical thing. So later, in few years after that, Samuel Morse created this Morse code system. Morse code system means depending upon the switching sequences, suppose one dot means you switch on a circuit and then switch off it after a short period. So that is your dot. And dash means if you switch on the circuit and keep it for a while, say for 3 times of the previous circuit, and then you switch it off, that is dash. So based on the combination of dot and dashes, you could make and break some electrical circuit, and depending upon the electricity that was coming in the receiver end, we could decipher that signal. But in that case also there was a problem. You can see now in this picture there is the transatlantic undersea cable, telegraph cables. So it is connecting between say New York and London, between two continents. Now such kind of cables are very expensive. You cannot put multiple number of cables. But in USA and both in England, there was multiple number of such outpost or input station, output station. You can say telegraph station in their terms. But the transmission channel is limited. Even in case of today's wireless communication, you have to buy some frequency channels. You have heard the term spectrum, 2G spectrum, 3G spectrum. So government leases such spectrums, and with different companies such as Geo, such as Airtel, they have to buy those spectrums or internet spectrums, network spectrums in a very large amount of money. Now, to minimize that thing, there was a need of such circuits that can transmit many inputs into one channel, not simultaneously. In simultaneously is possible in some cases like frequency division multiplexing, but in case of time division multiplexing, that is the scope of our experiment here. We can see that there will be some multiple inputs, and out of those multiple inputs only one output will be selected. That is the job of the multiplexer circuit. And in the demultiplexer circuit, the exact opposite thing happens. We get one input, and that may be displayed in many of the input channels, in one of the many input channels. So this is the circuit. You have seen this in your manual, that there are multiple inputs. It goes through one output, that is your single communication channel. It is wired or radio, that is mentioned in here. And in the demultiplexer, the same signal that is getting demultiplexed, it will be displayed in different output channels, original input signals. So this is a method of using our communication channels in more resourceful and more efficient way. Now let's look. This is the multiplexer circuit, as you can see. Now this is a 4 cross 1, that is 4 input and 1 output system. D0, D1, D2, D3, these are input channels or input signals. And how we can select them? Now as we said, 0, 1, 2, 3, we have 4 such values here. Now to in a digital system or in an electrical system, to include them, we need some numbers. And here we have two selector switches, that is S0 and S1. Based on the combination of this high and low or 0 and 1, we can make 4 input channels, 4 combinations such as 0, 0, 0, 1, 1, 0, 1, 1. So you can in generalized way you can say, if we had n number of selector switches, then we could have made a 2 to the power n cross 1 output channel or a multiplexer circuit. How this is happening? Because for S0 we have two, this is all are independent inputs and independent selector switches. So if we have S0 here, that has two status, on and off. S1 also has two combinations, on and off. So 2 into 2 into up to n terms, where n is the number of selector switches. Here the number of selector switches is 2, and so 2 square, we have 4 input channels and 1 output channel. Now this is the combination that I have discussed here. Now in the if doing experiment, you may have some confusion 0 1 and 1 0. So that is why I have created this table for you. If you notice here 0 1 1 0, that depends on the status, such as S1 is the most significant bit. Most significant bit means it has more weightage. More weightage means, suppose I am saying a number 34, then 3 is multiplied with 10 in decimal system, and 4 is multiplied with just 1. So similarly here you can see the output number, that is 0 1 2 3 D0 D1 D2 D3, that is depending upon more, it has more weightage on the S1. So S1 हम लोग पहले लिख रहे हैं और S0 बाद में. And in the manual or in the observation table, it may be written sequentially S0 S1. In that case you have to remember there 10 means D2 and 01 means D1, but physically this is happening, this table is always true.
Circuit of 4
Now
input
this
and
is the
1
circuit.
output multiplexer. As you can see, Y is the output and D0, D1, D2, D3, these are inputs. Now I have made this circuit in a simulator, online simulator. Now here two selector switches S1 and S0, they are off, and all the switches are now off, so the output is also off. Now for this condition, when S1 and S0 both are 0 0, if we keep D0 on, we will see both the LEDs are glowing, both the lights are glowing. If D0 is on, Y is on, D0 off, Y is off. So this is happening. Now in any of this case, if I change D1, there is no change in the output. If I change D2, there is no change in the output. If I change D3, there is also no change in the output. Now if I close D0, we can see the same pattern. I change D1, no change in output Y. If I change D2, no change in output Y. If I change D3, there is no change. So we can say for 0 0 condition, that is S1 0 and S0 0, that output is becoming similar, equal to the D0. Now if I change the status, that is 0 1. 0 1 means S1 is 0 and S0 is 1. In this status what happens? If I change D0, there is no change. But if I change D1, the D1 is now selected. D1 is now selected in the output. If I change D2, there is no change. If I change D3, there is no change. Similarly. Now, so that is the case. Now, if I change the status to 1 0, in 1 0 means S1 1 and S0 0. So, in 1 0 case, for our logic, D2 should be selected. Let's see what happens. If I change D0, no change in the output. If I change D1, no change in the output. If I change D2, now, yes, the output is now changing, as we can see. And for D3, there is no change in the output. And how this circuit is made, if you see, these are toggle switches, as same as the input switches that you consider. The LEDs are they look like bulb, but actually they are LEDs in your experiment. And if you see, the output is single output here. And for 1 1 status, what is happening? For 1 1, no change in D0, no change in D1, now no change in D2, but if D3 is changed, the output is glowing here. When the LED is blue, it means the LED is glowing. So we have noticed the changes. Now in this circuit, you will notice when the some status are being changed, it becomes, if it is 0, the line is white, and if the line is 1, then the line is blue here. So this is how they have represented it.
Okay, so that was your multiplexer circuit, and after that we will show the demultiplexer circuit. I have done a similar simulation, but the thing is, in demultiplexer circuit, in our experiment, the circuit is made in the negative logic. You will see in the next circuit.
So this is a one input and four output demultiplexer circuit. Here what I have done, there is a signal that is coming from the multiplexer output, that is E. And in the our actual circuit in experiment, we can control this via an independent switch. But here for the sake of representation, I have connected it with a clock pulse. Now if you see, at this case, S1 and S0 both are 0, right? So when S1 and S0 both are 0, this means the change in E has to be reflected in D0. This is the purpose of our demultiplexer. For 0, 0, we will get D0. So that is why here the change in E, that is getting reflected in D0. Now if I change the status from 0, 0 to say 0, 1, then these two LEDs E and D1 is blinking here. E and D1, because the status is now 0, 1. Similarly, if we do 1, 0, for 1, 0, we will find that E and D2, these two LEDs are blinking here based on the status of this. And if I keep it 1, 1, the status is here D3. And you will notice that whenever one switch is selected here, because of the negative logic, the unselected switches always remain glowing. In this status, when 1, 1 is there, the unselected switches are D0, D1, D2. They are always glowing and there is no change. If I make the change the status, that is 1, 0, now D2 should be glowing. Yes, now D2 is glowing, but D0, D1 and D3, they are not glowing. And for 0, 0 status, D0 is glowing, D1, D2, D3, they are not glowing. So these not glowing, this glowing but not changing status, it is the don't care condition here. How it is happening? First of all, there are three layers of inversion of input. First, all inputs are getting inverted, and in the last stage, that is also, you can see this is not a NAND gate. This is not a AND gate. This is NAND gate. Because of this NAND gate, what is happening? The don't care condition or the unselected switch, that has inverted. So instead of 0, now it is giving 1. But the status will be changed in only one case, that is the selected case. And the status will be exactly same or synchronized with E. So this is analogous to a system where you have a remote and you have some signals coming through for your TV channel, and you are trying to watch only one of the channels out of many channels. So based on these selectors, that is a remote control, based on these remote switches, you can uh, turn on any one of the channels and it can be displayed over your TV screen. So here D0 is being displayed and D1, D2, D3, these are static, these are not changing and these are not selected. So you can write it at 1, but 1 here means the LED is glowing but the output is not selected here.
Okay, so this also has been done here. Now the next thing is, this is the actual circuit. In the top left, there will be a supply that is simply like a mobile charger. It will give 5-volt DC supply to this circuit. And here you can see, in this region there is, we have now the circuit connected, that is here multiplexer, and in the opposite side, in the right side, we have demultiplexer side. The circuit is exactly same what I have shown previously in previous slides. Now here we have some input channels. These are independent input channels, and at the top we have output channels, independent output channels. So during the experiment, you can connect anywhere as you wish. And this is a sample of apparatus table, how it should be written. It is not necessary to write the specification for the patch cords. The quantity is just same, 7 to 8, and if you feel, you can modify this as per as your choice. And in the demultiplexer multiplexer circuit, it is a trainer kit made by NV's Tech, and specifications are there. You can also add the maker's number depending upon whatever the instruction is given in future by other teaching assistants. And this is a sample of the readings. Now you will see, for the multiplexer circuit, we have total 6 switches, 4 input switches and 4 input switches and 2 selector switches. So there are 2 to the power 6 combinations, that is 64 combinations. Now you can write 64 rows of 1010, but that is very cumbersome, that is very illogical. So what I have taught in my classes, that you write the status of selected switch as 1/0. it is combining two states together. So for 0 0 case, here you can see in the first row, for 0 0 case, d0 is 1 oblique 0 and y is 1 oblique 0. If d0 is 1, y is also 1. So it is happening like that. For d1 and d2 and d3, that is, I said, that is don't care condition. In don't care condition, there is no change. So you can say whatever be the status of this d0 or d1, whether it is 0 or 1, the output is not affected by this. So we introduce another third state, we call it don't care condition, and we are writing it as x. You will see the student here, he has written the physical significance of x. That is, the switch is not selected, the LED is not glowing in the first case. In the second case, here it was not mandatory to consider don't care condition, because here you see only three combinations, three switches, and 8 combinations are possible. That could be written as 0 1, but still he has considered here don't care condition as x, and here x means the switch is not selected but the LED is still glowing because of the inverted logic. So this is one way. Instead of 64 rows, now we condensed 16 cases in one line. That is 2 case, and here also 2 into 2 into 2. That is 2 into 8. 16 cases are condensed in one line, and 16 cases are condensed in the next line. So 64 cases can be compared in 4 lines. And you will notice this X thing that will be used again in K-map. There is a topic called K-map, Carnot map, which you will be learning in this semester, probably in the end of digital electronics. There they do, suppose they have a very big Boolean logic system or a very big truth table. Now, if the number of operation is high, then the circuit complexity will be more. To make that circuit, you will need more AND gate, more NOR gate, more NAND gate. So to minimize that, they have made such a system where they try to find some tendency or some generalization to specialization. Like if there is some trend, if we can minimize the circuit. So you have here minimize the circuit based on the trends, that only one switch is selected and others are remaining in don't care condition. Okay, so that is the thing. Thank you for listening.